Hello everyone, welcome to this lecture on Bootstrap and Linear Regression for the course Stat 3150, Statistical Computing. The objectives for this course are to understand the difference between resampling cases versus residuals, which refers to two different ways of using Bootstrap with linear regression. So in the last two modules, we reviewed linear regression and then we discussed residual analysis. And in particular, we talked about the linear regression assumptions and their relative importance, the fact that they're not all created equal and some of them are more important than others. In this module, we'll discuss how to use Bootstrap in the context of linear regression. And there's actually two different ways, as we'll see, of using Bootstrap. And those two ways correspond to two different sets of assumptions concerning the data generating mechanism. And that's the reason why we're discussing this is that it is a very common theme when using Bootstrap in more complicated settings. The idea is that you want to try to mimic the way the data is generated or the way the data is collected. And very often you'll see that you have potentially different ways of approaching the same problem. And so we'll look at this one, linear regression, where we actually have two different ways, at least, to approach the problem. Okay, so when the error terms in linear regression are assumed to be normally distributed, we know the distribution of the estimator beta hat. We can actually derive it. It follows a normal distribution with a mean beta and with variance sigma squared over x transpose x to the power -1. And well, I guess the inverse of that matrix, right? Remember, beta hat is a vector here. It's not a single number, and so it has a variance-covariance matrix. And under that assumption, we can use this result to compute p-values and confidence intervals. When we don't know the distribution, however, or if we don't want to assume it follows a normal distribution, Bootstrap is one way to make to have valid inference and compute p-values and in particular confidence intervals. As we discussed in the previous lecture, the assumption of normality is not a critical one, but sometimes when you have very skewed distributions for the outcome variables or for the residuals, you can account for that extreme skewness using Bootstrap. But you'll see that often it's going to be the case that the results you get from Bootstrap versus the results you get from assuming a normal distribution will be similar. Okay, and we'll see there's two different ways, as I've mentioned a couple of times already. And we'll refer to those two different ways of using Bootstrap as resampling cases and resampling residuals. Resampling cases is probably what you would have guessed if I told you to use Bootstrap and linear regression. Resampling residuals is a bit more different. And the main difference is how many assumptions we want to retain. And so resampling residuals in particular means that we need to assume additivity, linearity, and homoscedasticity. And in both cases, we still need to assume independence of the errors. And I'll come back to that idea at the very end. So the key point is that there's a difference in how many assumptions we want to make or how strong we want to make those assumptions. Okay, resampling cases. That's the first one we'll look at. And as I mentioned, it's the simplest form of Bootstrap for linear regression. For this form, what we do is that, well, first of all, we only assume that the errors are independent. It's the only real assumption we're making here. And it can be shown that when resampling cases, the Bootstrap estimates of the standard error will be approximately equal to the Eicher-Huber-White robust standard error that we discussed in the previous lecture. So here's the algorithm. We're going to sample with replacement from the set of vectors yi, xi. So we're resampling the rows of our data set, essentially. And then for each resample, we refit the linear model using the Bootstrap sample, so the resample, and then we get new Bootstrap estimates beta hat b. And we repeat this 500, 5,000 times, however many Bootstrap samples you want to use. Okay, so let's look at an example of how you can do this. We're going to focus on an example that we've already looked at from the DAAG package. We had this dataset iron's lag that was containing information about iron content measurements using two different methods, so a magnetic method and a chemical method. And so here we're fitting this model, so LM of magnetic tilde chemical, comma, data equals iron's lag. So that's our first fit. That's our beta hat. Next, we're going to do Bootstrap. We'll start by recording how many rows we have in the iron's lag data set. And then we're going to replicate a code block 5,000 times. Inside the code block, this should be very familiar. We've already looked at code like this. Remember, we want to resample the rows. And so we're resampling the indices effectively. So we use sample of n, replace equals true. And then we're using fit boot. We're creating fit boot, which is LM of magnetic tilde chemical. So the same equation. And next, the only thing that changes is the data set. So we have data equals iron's lag, bracket, indices, comma, bracket. And finally, the output is the coefficient estimates. So we're using the function coef to extract the coefficient estimates from that Bootstrap model fit. And then we repeat this 5,000 times. So what we get in the end is a matrix with 2 rows. Each row corresponds to a different regression coefficient. And then 5,000 columns. Each column corresponds to a different Bootstrap sample. And you can see we even retain the names of each coefficient as row names for our matrix. Right? We get intercept and chemical. Okay? And so from this we can compute the standard errors for the intercept and the slope using the sample standard deviation for each row separately. So SE underscore int, standard error for the intercept, is SD of boot beta 1 bracket 1 comma bracket. And similarly for the slope. Okay? We could also estimate the biases if we wanted to. But it is known that you don't need to rely on the normality assumption to show that actually beta hat is unbiased, right? We know and we can show easily that beta hat is unbiased. And so here we're not estimating the bias. Okay, so next what we're doing here is computing the confidence interval using a Bootstrap normal confidence interval. You could use a pivotal or a basic Bootstrap instead if you wanted to. And here I'm using cbind because I'm going to get different values for each of the coefficients. And so when I compute lower, I get a vector, and I want to stack them as columns in a matrix. And so the output here is shown below. We get for the intercept, we get from negative 3.27 to 6.07 or 0.8. For chemical, we get 0.6725 and 1.16. And you can check that this is actually pretty close to the Eicher-Huber-White confidence intervals that we derived in the previous lecture. And of course, we can compare it to what we get from least squares estimation or maximum likelihood estimation. And we get these things here. So the confidence interval for the intercept is a bit smaller, but still includes 0. And on the other hand, the confidence interval for chemical is comparable to the one from NLE theory. So just like we concluded by using the Eicher-Huber-White standard errors, the confidence intervals actually don't change very much. Okay, so that was the first approach. The second approach is a little bit more involved. We call it resampling the residuals. And this approach actually requires a bit more assumptions. We need to assume additivity and linearity, and also homoscedasticity. But the trade-off is that we get smaller confidence intervals typically than if we had resampled the cases instead of the residuals. So that's the trade-off here. We make more assumptions, but we may get smaller intervals. here's the algorithm. So it starts by fitting the model, just like we did earlier, and then computing the residuals and the fitted values. I'm going to call the residuals EI here, and the fitted values YI hat. So the first step is to sample with replacement from the residuals, and what we get is a bootstrap sample of residuals. I'm going to call them E1B all the way to ENB. Next, we add the bootstrap residuals to the fitted values to get bootstrap YIs. I call them YIB. So YIB is the fitted values from the original model plus the bootstrapped residuals. And now what we essentially have is new outcome variables, and we use those new outcome variables and the original covariates to fit the linear regression model and obtain bootstrap estimates of beta hat B. So that's why we call it resampling the residuals, because the resampling happens at the level of the residuals, and then we build new outcomes out of this. But the x's here are fixed. That's the key thing. Okay, so let's look at how we could do this in R. We're going to use the second example that we've looked at before. Recall that for this example, with the mammal's body and brain measurement, we concluded that additivity and linearity hold, and also we didn't see any evidence of heteroskedasticity. So we should be comfortable resampling the residuals here because we've done the residual analysis and we've concluded that those assumptions are probably met. Okay, so coming back to the code here, first I'm creating this data set where I transform those two variables, log body and log brain, and then I'm fitting the linear model, log brain tilde log body, comma data equals data set. Next, I need to compute the residuals using the function resid. And then I'm keeping track, as usual, of how many, what's the sample size. So n is going to be the length of the residuals, which is the same as the number of rows in dataset. So finally, we can do Bootstrap. So the code block we're going to replicate starts by sampling indices, just as before. And now on the next line, this is where we're creating the new outcome variables. So log brain boot is fitted fit2, which is the vector of fitted values, plus the bootstrap residuals. So we're using resids, bracket, indices, bracket. So those are the resampled residuals. So once we have our new outcomes, we can fit the model. Here I'm using LM brain, LM of log brain boot. So those are the new outcomes. Tilde log of mammals $ body. Here I'm not using the data equals dataset argument because log brain boot is not a variable in the dataset. It's a variable outside of the dataset. So I'm not using that argument. Here I'm using log of mammals $ body. You could also write dataset $ log underscore body. Both would be equivalent. And finally, once we fitted the model to the bootstrapped outcomes, we can extract the coefficients using coef. And this is what we get out of the bootstrap code block. And we replicate this again 5,000 times. As before, what we get is a matrix with 2 rows corresponding to each coefficient and 5,000 columns corresponding to each bootstrap sample. And we can construct confidence intervals just like we did before. We're computing first the standard errors. And next, we can compute the confidence intervals, the lower bounds and the upper bounds. And this is what we get. So the confidence interval for the intercept goes from 1.95 to 2.32. And the confidence interval for log body goes from 0.69 to 0.81. Or 0.70 to 0.81. How does that compare to MLE theory? Well, we can see that we get, again, essentially the same results as we got from Emily theory, but the Bootstrap confidence intervals are slightly smaller, so slightly narrower, meaning that we can be more confident in our results. Okay. Note that other types of residuals could be used for this. We didn't really talk about the other types of residuals, but you'll probably talk about them in other courses. And this would have the effect of mitigating the impact of outliers on the outcome. But the key thing to keep in mind is don't use the standardized residuals. You want the residuals to retain about the same variance as in the original data. So if you do use other types of residuals, or you see people use other types of residuals, make sure they're not standardized. Okay, so this is two different ways of performing Bootstrap in the context of linear regression. And we talked about resampling the cases and resampling the residuals. Resampling the cases is valid more generally, but resampling the residuals can lead to smaller, more accurate confidence intervals. And as I mentioned, deciding which approach to use is a question of how much you trust the model, because you need to make more assumptions if you're resampling residuals. And you can also see how they correspond to two different ways of collecting the data. For example, if you fix the design matrix and then you collect outcome variables, this would correspond to what you get by resampling the residuals. So think of an experiment where, for example, you give a placebo and a treatment to a fixed number of patients. So those numbers are fixed by design, and then you compute the outcome of interest on those patients. This would be different from a setting where you would collect all the y's and the xi's at the same time without necessarily designing the covariate matrix first. And this would correspond to what you get when you do the resampling of the cases. So Bootstrap is really, the different types of bootstraps correspond to different ways of thinking about the data generating mechanism. And then the final remark is that neither approach is valid when you have correlation between the error terms, because we're assuming that our rows are independent in our data set. When is it the case that the errors are correlated? Well, it happens when you have clustered data or repeated measurements or time series data. Bootstrap can actually be adapted to these methods, and I encourage you to look it up if you're interested, but this is beyond the scope for this course. But just remember that what we've looked at assumes that the error terms are independent.